Welcome everyone, and thank you for taking the time to join tonight's webinar, Teaching Writing in AP Physics 1, presented by leading physics educator and experienced AP Physics 1 teacher, Martha Lietz. I'm your host, my name is Thomas Mena, and I'm the STEM Marketing Manager here at BFW High School Publishers. Here you'll see an agenda for tonight's program. The bulk of the webinar will be the presentation followed by Q&A. We hope to wrap things up no later than 7 p.m. If you have a hard stop at 7 p.m., though, not to worry, if the webinar is still going, you'll be sent a full recording later on. There are many attendees, so everyone is muted and will be muted throughout the webinar. As mentioned, we will be emailing a follow-up to this webinar with its recording along with the slide deck. So don't worry if you miss something or need to step away for a moment. Please allow a couple of days or so for us to send that out, but be sure to check your spam folders if you don't see it after a few days. For questions, and this is very important for the Q&A section of the webinar, you should all see a chat function on the GoToWebinar toolbar. In the chat function, write your question and then choose the option Send Question to Staff. This way the questions will get sent to me so I can read them out loud for Martha to answer during the Q&A portion, and in some cases I can even answer them myself if I know the answer. Feel free to send questions in at any time during the webinar, and I will do my best to parse them out during the Q&A section. Since there are many attendees, it is possible we may not get to all the questions. If we don't get to your question, don't worry, we'll do our best to address anything that goes unanswered in our follow-up, which will include an extended Q&A document if needed. Also, feel free to send any unanswered questions directly to hsmarketing@bfwpub.com and we can look into them. For sales-related questions, especially about college physics for the AP Physics 1 course by Gay Stewart, things like price quotes, ordering information, digital options, feel free to contact your sales rep. If you're unsure who your sales rep is, you can email hsmarketing@bfwpub.com or visit go.bfwpub.com/findmyrep. Your rep is a resource for you and is always happy to talk to you about our books and answer any questions you may have. Now, it is my pleasure to introduce our presenter this evening. Martha Lietz has been teaching AP Physics at Niles West High School in Skokie, Illinois since 1990. She earned her National Board Certification in 2009. Martha is an AP consultant and has served as a Table Physics Development Committee member from 2001 to 2005, and again from 2010 to 2012, a Physics 2 Development Committee member from 2012 to 2016, and an AP Physics reader since 1997. She has served as the chair of the American Association of Physics Teachers Committee on Physics in High Schools. She has also served as an author and editor for several College Board curriculum modules and for the new AP Physics 1 and 2 Inquiry-Based Lab Guide. She is the co-author of the Teacher's Edition for our landmark textbook by Gay Stewart, College Physics for the AP Physics 1 course, 2nd edition. So let me be the first to say thank you to Martha for her time tonight, as well as the time she spent preparing this webinar for us. And without further ado, Martha, I will pass the screen to you and we shall get started. So give me one moment here to do that. And great, we can see your screen, so ready when you are.
Thank you, Thomas. I will start with a very brief introduction to the AP Physics 1 course for those of you out there who are contemplating offering it at your school or who will be teaching it for the first time next year. So AP Physics 1 is designed to be an algebra-based college-level course comparable to the first semester of a pre-med physics course. This is to contrast it with the Physics C course, which is a course directed at scientists and engineers. The topics included in AP Physics 1 are kinematics, dynamics, including circular motion and gravitation, energy, momentum, rotation, simple harmonic motion, electrostatics, circuits, and waves. For a more detailed description of what is included in the course, I refer you to the new course and exam description. Students who do well on the AP Physics 1 exam can generally expect to get 1 semester of college credit for their work, depending on where they intend to go to college. It is designed to be taught as a first-year course with no physics prerequisites. Here's a quote taken directly from the new course and exam description about the goals of the AP Physics course. Those goals include not only a deep understanding of the physics concepts covered, but also developing an ability to reason and to communicate their reasoning to others. AP Physics 1 students are expected to explain relationships, apply mathematical routines, and justify the use of mathematical routines they are applying. Thus, they need to be able to write about physics as well as use equations in their reasoning. The exam itself is 3 hours long, 90 minutes of multiple choice and 90 minutes of free response. One of the questions requires the students to write a paragraph-length explanation of a physical phenomenon. And we will be discussing training students to write these paragraphs in this webinar. But other parts of the free response exam require brief written explanations or justifications. So some of what we will be talking about is applicable to those questions as well. The College Board provides a one-page document that describes the style of the question and the expectations of the response. The link at the bottom of the slide here will take you to the document itself. So just to read a few sentences from that, a paragraph-length response to a question should consist of a coherent argument that uses the information presented in the question, proceeds in a logical expository fashion to arrive at a conclusion. The students need to demonstrate their ability to communicate their understanding of a physical situation in a reasoned expository analysis. The response needs to be coherent, organized, and a sequential description of the analysis of a situation. It should make sense on the first reading, and it should be of moderate length, not too long and not too elaborate. The more information on this page includes how the students can earn points for their written work. They can earn points for correct physics principles. They may not earn points for lengthy digressions, principles not presented in a logical order, or primarily equations with little explanations. The explanation may include diagrams, graphs, equations, but should refer to them in the prose of the paragraph. Examples in standard textbooks can provide a model as to how to compose an argument that has both prose and equations and diagrams. So let's take a look at a specific question from a prior exam. Many of you have seen it and maybe use it in your class already, but I won't assume that everyone listening has seen it. If so, I'll read through it for you. The figure on the left shows a uniformly thick rope hanging vertically from an oscillator that is turned off. When the oscillator is on and set at a certain frequency, the rope forms the standing wave shown above on the right. P and Q are 2 points on the rope. The tension at P is greater than the tension at Q. Briefly explain why. And part B, a student hypothesizes that increasing the tension in a rope increases the speed at which the waves travel along the rope. And here's where the coherent paragraph language comes in a clear, coherent paragraph length response that may also contain figures and/or equations. Explain why the standing wave shown above supports the student's hypothesis. So if this were a face-to-face teaching situation, I would ask you what concepts you think are important for a paragraph response to part B. So if you want, you can think about that for just a moment and maybe jot some equations down on the page. Clearly, we need to discuss the tension and the speed, not to mention the relationship between speed and wavelength. We want the students to talk about how the wavelength at Q is shorter than the wavelength at P, and then speak about how the frequency is the same everywhere in the rope. This means that the speed is proportional to the wavelength. Thus, point P, where the tension is greater, also has a greater wave speed. So now let's take a look I'm clicking on the wrong spot. Need to go, there we go. Oop, too far. Here's the rubric, and we can see that that's exactly what they get the points for. Notice that the first 4 points are all for physics concepts, observations of the wavelength, the frequency being the same, the equation V equals F lambda, and for indicating the tension is greater at the top than at the bottom. And the last point in the rubric is for writing a coherent argument in paragraph form. So the question is, how do we teach students to compose this paragraph? So many teachers use what's called a claim evidence reasoning framework. The claim in a physics context is usually a comparison. In this case, tension, or a relationship in this case, wave speed and tension. But sometimes it's a comparison, like which block gets to the bottom of the hill first, and so on. Evidence is physics principles in some representation. So a graph, an equation, a free body diagram. And the reasoning is a verbal explanation as to how the evidence supports your claim. Now, I've modified this a little bit in my classroom to become an evidence reasoning conclusion problem or process. My experience is that the students, when they see claim evidence reasoning, they say, I'm going to pick an answer and then I'm going to support it, because that's what they do in some of their other classes. They decide, well, should we have a nuclear power plant in Skokie or not? And they pick the yes or the no, and then they support it. Whereas in physics, there's usually a right answer, and it's not guess and then support your guess. I want them to start with the evidence and reason from the evidence and then come to a correct conclusion. I don't want them to just go with their gut reaction and justify it. I want them to look at the evidence first and then support it. So I've modified it a little bit to be evidence, reasoning, conclusion. So let's start with a simple example from kinematics. A ball is dropped from the top of a tall building of height h. It falls from rest, accelerating uniformly until it strikes the ground below. How does the time it takes to fall the first half of the distance from h to h/2 compare to the time it takes to fall the second half of the distance? In other words, from h/2 to the ground. So this one is an example of a comparison. So the first thing to do is to have the students possibly create multiple representations of this physical situation. They can create position time graphs, velocity time graphs, motion maps, a kinematics equation. In the early part of the year, you may want to have them plug in some numerical values to confirm what they think is the correct answer. And the first time you do this, you want to model the process for them. You may want to have the students create these representations on whiteboards and then share them in groups to make sure that their evidence is correct before moving on to write a paragraph that refers to the evidence. I like to take pictures of their whiteboards and then put them up on my website so that they have them for reference later. So here are 4 different representations of this particular physical situation. So, whoops, somehow I moved, there we go. Click on the laser pointer here. Here is a position versus time graph. The object falls from rest, so it should start with a slope of 0 at a height h, and then since it's constant acceleration, it should be a parabola going downward until it hits the ground. Here is a velocity versus time graph. Again, it starts from a speed of 0. We've chosen up as our positive direction, so the velocity is increasing in the negative direction, and so we have a straight line, constant acceleration on the negative velocity side of the time axis. Here is a motion map. A motion map shows a dot to indicate that the object starts from rest, and then has arrows that represent the increasing speed as the object falls toward the ground. And of course, there's the delta x equals v initial t plus 1/2 at squared kinematics equation, which then can be modified to fit this particular situation with initial velocity 0 and an acceleration of negative g to get the delta x equals negative 1/2 negative gt squared. So now let's compose the reasoning and conclusion from these different representations. So here's the position versus time graph. In the reasoning part, the students should write sentences about the evidence, and it might even help to annotate the graph a bit as I have shown. So for example, add a line at h/2 to show the half the height, and then draw a horizontal line to intersect the position graph, and then show that that actually hits after time t/2. And then students should write a sentence that says the graph of the position versus time is a parabola since the object is falling with a constant acceleration. So they're justifying the shape of their graph. As can be seen in the graph, the ball reaches a height h/2 at a time greater than t/2, where t is the time for the total fall. So that would be the reasoning portion. And then the conclusion is, thus, the time to fall the first half is greater than the time to fall the second half of the distance. The students could also reason with the velocity versus time graph. So to annotate that graph, I might draw a line at t/2 and then talk about how the area before t/2 compares to the area after t/2. So a sentence that you could write, or a couple sentences you could write, the students could write, would be the displacement is equal to the area under the velocity versus time graph. T is the time to fall the distance h. As can be seen in the graph, at t/2, less than half the distance has been covered. And since A1 is less than half, A1, this area of the triangle, is less than half the total area. So that's my reasoning. And then my conclusion is the time to fall half the distance is more than half the total time. You could also conclude by stating that falling the first half of the distance takes more time than falling the second half of the distance by trying to draw a line in here that would approximate where would you have half the distance in the triangle and half the distance in the trapezoid. Of course, the student does not have to reason both from a position graph and from a velocity graph, but it's important to show the students that they can come to the same conclusion from different pieces of evidence. And the last one we can talk about for this particular example would be the motion map. So here's the motion map. I've labeled h/2. In the motion map, each arrow represents the same amount of time. The arrows get longer as the object falls faster. And so that's where you're showing the reasoning part, where the students indicate they know that there's an acceleration here and they're demonstrating the acceleration. And then they can reason, if you look, you see that there are a dot and 3 arrows before h/2 and 2 arrows after h/2. So there are more arrows for the first half of the fall. So it takes more time to fall the first half. Okay, so one way, when students are just beginning to learn how to write these CER essays, you can give them some scaffolding. You can give them a page with a space for the evidence, a space for the reasoning, and a space for the conclusion or the claim. So here is a handout available with the teacher's materials for this text that has that exact question: space for the evidence, space for the reasoning, and space for the claim or conclusion. So again, I want to reiterate that we start by modeling the process for them, just like we do for drawing free body diagrams, motion maps, and any other process that we work for them. Then we progress to simple prompts with scaffolding, like the different sections of the page. We may even want to let them work in groups and whiteboard their explanations. If you can find enough prompts, You could give each group a different prompt, each group a different comparison, and have them whiteboard the CER explanation and present it to the rest of the class. I like to take a picture of the whiteboards of each individual different question and again, post them on the class website. Gradually, you'll progress towards more autonomy, individual work, no specific directions about where to write things, and so on. I would advise that you don't put these types of questions on a test or on a unit summative assessment until the students have had plenty of practice, or you may have an open revolt on your hands. Here's another example. Once the students are adept at writing the paragraph length responses, you can have them create the rubrics as well. Here's a question I got from Alan Van Huvelen's Active Learning Problem Sheets. Identical constant forces continuously push blocks A and B from the start line to the finish line. Both blocks start from rest. Block A has 4 times the mass of block B. Assume friction is negligible. Which block has the greater change in momentum? Block A, block B, they have the same change in momentum. And then include the standard text, justify your choice in a clear, coherent paragraph length response, which may contain equations or diagrams as necessary. Let's take a look at an accurate response to this question and then delve into how to create a rubric for a question like this. So here's a paragraph. According to the impulse and momentum theorem, F net delta T equals delta P. The objects have the same net force exerted on them. Thus, the block that takes a greater time, delta T, to cross the finish line will have the greater change in momentum. Since delta X equals 1/2 AT squared, and both objects move the same delta X, the block with the smaller acceleration will take a greater time, delta T. Because A equals F net over M, the block with the mass 4m will have a smaller acceleration. Thus, block A will take a longer delta T, have a greater impulse, and thus a greater change in momentum. It's important, I believe, to train students to use equations as words in sentences. It's not necessary for them to write the words for, quote, net force times time interval is equal to the change in momentum, unquote. They should just write F net delta T equals delta P. It's simpler, it makes it shorter and clearer and easier to understand. In this case, the evidence is in the form of equations such as the impulse momentum theorem, the constant acceleration equations, and Newton's second law. And the reasoning is the sentences referring to the mathematical models. The conclusion is the last sentence. Now, there may be other correct solutions to this that utilize other physics principles or representations, but since time is limited, I'm only going to work with this one. Once I model a correct solution for the students, I would highlight the key concepts for them. I have highlighted here in yellow the key things that I think need to be said about this question, or the key pieces of evidence. And I have highlighted in green the conclusion statement. So in particular, the impulse and momentum theorem is a key piece of physics that needs to be addressed. The kinematics equation relating the distance and the time and the acceleration is key. And Newton's second law relating the force and the mass to the acceleration. And here the conclusion statement I have highlighted in green. And here is one way that these important statements can translate into a rubric. There are 3 points for the physics concepts, 1 point for the correct conclusion, and 1 for clear, coherent paragraph. Notice the phrasing on the rubric. The point isn't just for the equation, it's for correctly reasoning with the equation. Again, for correctly reasoning that the object with the greater acceleration will take less time. And that would include stating the equation. And for correctly reasoning from Newton's second law that the object with the greater mass has a smaller acceleration. The points aren't just for the equations, the points are for the reasoning that goes with the equations. And where was I? Okay. So each of the physics points, as mentioned in the single pager about the paragraph length response, the argument may include equations, but cannot solely be a mathematical derivation. So just for fun, here's a counterexample. This is a completely correct analysis applying impulse momentum theorem, the kinematics equation, and Newton's second law, first for object A with mass 4m, second for object B with mass m, and coming up with a larger value for the change of momentum of A than for B, and thus a conclusion that change in momentum A is greater than change in momentum B. The same physics is there, and it's correct, and would be sufficient for one of the other short answer questions, but there's no prose to support the equations, so this response would almost certainly lose credit, and a lot of credit, if presented for the paragraph question. Once you have modeled the process I just showed you for the students, you can then have them create the rubrics. So first you would provide a prompt to the students, give the students about 10 minutes, maybe 13 minutes, depending on the prompt, to write a paragraph length response. And then have them identify the important statements in their paragraph. Based on these important statements, they can create a rubric. And then they can trade and grade each other's paragraphs. Here's an example of a sheet one of my colleagues uses with his students to help them build a rubric. They can write the paragraph, highlight or asterisk the key points, and from that create the rubric. This gets them thinking about what is the important physics going on in the problem. When the students engage in the metacognitive process of evaluating their own writing and their peers' writing, they begin to write stronger paragraphs and make stronger, more coherent arguments. You could, in this format, have the students cut off the bottom of the page and keep their own rubric and then trade their answer to a different person who would then grade it according to their own rubric and then share together what their grading and what they thought was important in the paragraph length response. So the Stewart text provides lots of resources for your efforts to train your students to write these paragraphs. There are handouts of the teacher's resource materials, which are referenced in the teaching tips in the teacher's edition. The student edition has AP practice problems at the end of each chapter, some of which are paragraph length responses. And there are 2 full AP exams in the student text, each with a paragraph length response question. So here is an example from the handouts, a friction and acceleration example. It's one I like to use in my dynamics unit. A block is moving up a ramp. There is kinetic friction between the block and the incline, and when the block reaches the highest point, it slides back down. Is the magnitude of the acceleration of the block greater on the way up, on the way down, or the same for both trips? Justify your choice in a coherent paragraph length essay, including free body diagrams. So early on in the year, I sort of forced my students to use free body diagrams. Before I did that, I found that the students who did use the free body diagrams were able to get the question correct, and those who did not were not. Here's another example from the teacher's resource materials. This shows you that the teacher's resource materials also include complete solutions to these reasoning and physics worksheets. This one is a reasoning and physics task related to forces and kinetic energy. In fact, it's almost exactly the same question as the momentum one we just used. A constant force pushes 2 objects, one of mass m and the other of mass 4m, for a total time delta t each, starting from rest. Which of the 2 objects, the larger or the smaller, has a greater kinetic energy at the end of the time delta t? Explain your reasoning in a clear, coherent paragraph length response. And this one again provides the scaffolding of the evidence section, the reasoning section, and the conclusion. Here's an example of an end of chapter practice free response question that is a paragraph question. So chapter 4, Again, on forces, short answer, 2 blocks, in contact, pushed by a single force. The students need to write a clear, coherent paragraph length response that compares the contact forces for these 2 blocks. The teacher's edition has the solution and rubric for this question. And here is a paragraph length question from the full sample exam. I think it's the first full, I can't tell, 491. So it's probably the second full sample exam, although I'm not 100% sure. As you can see, the teacher's edition has the question, where'd the mouse go? The question here. There we go. The question here, and then it has a rubric with points and a complete solution. So as you can see, the Stewart text and the ancillary teachers materials offer lots of opportunities for practice with your students. That's all I have for now. Thank you for your attention, and I will turn this over to Thomas now to facilitate the Q&A portion.
Excellent. Martha, could you skip to the last slide for questions? Perfect. Okay, so again, everyone, if you have a question, you can just chat them in the chat feature of the GoToWebinar toolbar. Chat your question and then send it to send question to staff, and then I'll get the question in. Some quick follow-up things though. Again, stay tuned for a follow-up email with this webinar recording, as well as the slide deck and a Q&A doc if necessary. For sales questions, again, I know Martha showed some examples from our Stewart program. If you have any questions about that, feel free to contact your sales rep. Again, if you don't know who your sales rep is, you can email hsmarketing@bfwpub.com, and then or go to go.bfwpub.com/find-my-rep. And of course, for anything else, if you have any questions after this webinar, or if you are someone who's watching the recording of this webinar and you have a question, you can submit that question again to hsmarketing@bfwpub.com. So I'll wait another minute here for some questions to come in. So far, not many have sent some questions in, which is fine. That means everything was nice and clear and good. Hopefully everything made sense. But a couple things I'd like to ask, Martha. You did mention initial scaffolding. So you said when students are beginning to learn how to write the CER essay or a paragraph length response, you said it helps to give them scaffolding. And then you showed an example of one of the worksheets that has like a space for evidence, a space for reasoning, and then a space for conclusion or claim. Could you just kind of talk about that again, or just kind of how you, your experience with using scaffolding in the classroom to teach the paragraph length response?
Sure. So I would give them that page that has those different sections, and then to start with, we might work together to develop the different pieces of evidence that we could use to talk about a particular phenomenon, and then we would put those in the evidence section. And then we would write sentences, or I would write the sentences on the board so that they knew exactly what words and how to put the words together. And we would come up with the reasoning section and put that in the reasoning section. And then we would write the conclusion in the conclusion section. And eventually, I would, instead of saying evidence and then have a paragraph, in parentheses right after evidence, the text, physics representations of this situation, or physics in some representation, I would just have the word evidence. And so I wouldn't tell them again what evidence is or what to do. I would have the word evidence, and then I would have the word reasoning, and then I would have the word conclusion. And then eventually I would work towards where I just gave them the prompt, and there was no section for evidence, no section for reasoning, no section for conclusion. They just had to know that they had to have those pieces to structure their argument, just like they would on the AP exam, because the AP exam doesn't put evidence, reasoning, conclusion statements on the question. They just tell the students to write a paragraph. So start out, so they get used to writing evidence, reasoning, conclusion all the time, and then just take away the words for the prompts, which are the scaffolding, and have them write the paragraph on their own.
Great. Okay, so that was a great answer and really clear. We actually did get a couple questions in, so I'll go ahead and ask those. We should be able to get to all of them, so folks who chatted them in, thank you. And keep chatting them in as you're listening here. So Barry actually asked, he said, do you have any opinion about students using point form to outline their quote paragraph length answer? So do you have an opinion about students using point form to outline their paragraph length answer?
I think that my opinion is that it would be fine for the students to write their prose in bullet point form, as long as each bullet point is a complete sentence and not just a phrase and not just an equation. So there was some discussion in the two committees as to what was acceptable and what was not acceptable in paragraph length response. And some people on the committee wanted to accept bullet points and some people wanted not to accept bullet points. And I think we finally discovered that the interpretation by the people who didn't want to accept bullet points was that it was just phrases like the phrases I showed in the PowerPoint. If they're complete sentences, then it should be acceptable to use bullet points, as, you know, so for the first point in an argument, like according to the impulse and momentum theorem, F net delta T is equal to delta P. If you write that as a full sentence and you have a bullet point in front of it, and then you write the next point as a sentence and you have a bullet point in front of it, if that helps the kids see how the points are delineated in the rubric, that's great. I've been known to tell my students to write their bullet point list and then just erase the dots, because there's no rule that says you have to have the first word of the second sentence on the same line as the last word of the previous sentence. So I don't think that, my opinion is that bullet points are okay as long as they are complete sentences and as long as it would read like a paragraph if you just erase the dots. I hope I interpreted your question correctly.
Yeah, I think that was a good answer. We did get another question in, Martha, that actually asked you to clarify that you just to clarify if you discussed evidence, representation, and conclusion as your method.
It was evidence. The evidence is the representations. So should I scroll back to where through the okay. Oh, I'm on the wrong. I'm gonna click on the right place here. So in this case, this is the evidence. The evidence is the representation. And so here is the evidence. This representation is my evidence that I am going to talk about. And it is appropriate to this problem because of the reasoning that I present over here. So it's evidence and then reasoning and then the conclusion. The representations are the evidence. So it's not evidence, representation, conclusion, it's evidence, reasoning, conclusion.
Okay, I think that definitely explained that framework. And again, I think also for the teacher who asked that question, we'll send the slide deck too, so you can also go back and review those specific slides on those.
I'm just scrolling back to your last slide for those people who want to.
Okay, and so let me see. I think we had one more question here. Okay, so one question that came up was if you could again just kind of recap your recap like motion maps, how you basically how you would explain that to the student, the motion maps.
The motion maps are an idea, and again, sorry for, I hope this isn't making people crazy going so fast backwards through the slides. Motion maps are a concept that comes out of the modeling program and the modeling curriculum, and other places. If you just Google motion maps and modeling, you will probably find a document that will explain to you how motion maps are used. And some of them have velocity vectors on them. Some of them, almost all of them, have velocity vectors. Some of them have acceleration vectors, although I haven't used that here. So there are a lot of different ways to do motion maps. I think there are also motion maps in the Stewart text, although I don't know what page that's on, and I don't have the text with me, unfortunately. It's across the room. So a motion map, a motion map represents an object that is stationary with a dot, and then each arrow represents the same time interval. So in this case, it might be 1/10 of a second. So the short arrow means that the object has not moved a very far distance in the first 1/10 of a second, and then it moves a greater distance in the second 1/10 of a second, and then a greater distance and a greater distance and a greater distance. So each arrow is supposed to represent the same time interval, and the fact that the arrows are getting longer indicates that the object is accelerating. And so so the arrows, the fact that it takes more arrows to go the first half of the distance implies that there is more time for the first half of the distance and less time for the second half of the distance. But if you know someone who uses the modeling curriculum, like myself, for example, sometimes, then you have access to handouts that talk about motion maps. And I believe they're in the kinematics chapters of the Stewart book as well. And there are different ways of using motion maps differently. So again, I'm not using the acceleration arrows here. So I just left that off of this particular evidence because it wasn't required for this justification.
Okay, that was a great answer there. So, okay, so we're almost at about time. We did not get we got a statement in. The statement said, and I would second this. It said, just a comment, great webinar, enjoyed it very much, and we'll definitely use your examples in class. So some praise for the webinar. We appreciate the comment. Thank you. If we have any other questions, we'll take another second here to chat them in. Oh, we just got another one. It said, would it be possible to use dimensional analysis in reasoning?
I don't think that is advisable. I think that dimensional analysis is a great way to check to make sure that an algebraic expression that you have derived has the right units. And so it's a good check to make sure that, the square root of 2 times h over g actually has the units of time, for example, but saying that, just saying you have to multiply meters per second times seconds to get time is not reasoning with physics. And it leaves out things like the factors of a half that show up. So I would not advise that you reason with dimensional analysis to prove a point. You would reason with physics concepts like Newton's second law, Newton's third law, and so on. And then if the students want to check their algebraic responses at the end, they could check them with dimensional analysis. But even dimensional analysis doesn't pick up on the fact that the fact that it's 2 square root of the quantity 2h over g rather than the square root of the quantity 3h over g, for example. That 2 or 3 isn't checked using dimensional analysis.
Great. No, that I'm pretty sure that definitely answered it. We got another comment that said, great webinar session and thank you. So With that, I just want to reiterate again, if anyone's especially listening to the recording here, if you have a question that wasn't brought up, feel free to email hsmarketing@bfwpub.com, or you can contact your sales rep. Thank you, Martha, bringing up the screen again there. You can see the email as well as the link where you can find your sales rep, and your sales rep can also help you with any questions about Stewart. If you're not familiar what the Stewart text is, definitely contact your rep. They can get you a copy of it as soon as possible. And with that, I just want to say thank you, Martha, again for your time and for a great webinar. And thank you everyone who attended the webinar as well as listened to the recording here. And have a great night. So thank you, everyone.
Thank you, Thomas. Good night.
Good night.